I Want Games is a crowd-funded series about research and applications of artificial intelligence in video games. If you like my work, please consider supporting the show over on Patreon for early access and behind-the-scenes updates. In part 1 of my case study on Horizon Zero Downgraded Games 2017 PlayStation exclusive, I explored how the game is built to create herds of eye-controlled machine animals. This requires a complex agent hierarchy system, where each machine can make decisions about how to behave using a hierarchical task network planner, but also groups agents together to dictate their roles and responsibilities as part of a herd. This is all part of a system known as the collective, which maintains the ecosystem of all machines in the world as you are playing it. In this closing entry, we are going to look more closely at the systems that each individual machine can utilize as part of their core behavior. This includes the likes of sensor systems, navigation for both land and air machines, and how execution of eye behaviors is heavily tied into the animation systems to give each machine an unsettling yet realistic behavior. So first up, let's take a look at the sensors used by machines to trigger eye responses, as well as how animation ties into the overall execution of their behavior. There are a significant number of unique sensors that a machine can use. Visual sensors, such as the watch's eye, to radar and proximity sensors on long legs. Aural sensors that hear explosions at distance to stone throws close by, as well as the ability to sense players colliding with them directly. Each machine has a collection of these sensors calibrated with their own sensitivity values, making it easier to sneak up on, say, a watcher, a grazer, but a lot more challenging to catch a stalker unawares. Now, a traditional sensor system might just enable for events to occur around an eye and they either see it, hear it, or nothing. But the sensor systems are actually a lot more nuanced. This is achieved through information packets that are attached to objects that can cause stimulus in one of the machine's sensors. This includes the player, other NPCs, rocks, fire darrels, other machines, and wildlife. This data tells the receiver, the machine that sensed something, information about what it is that it detected in this state. Hence, machines as well as human NPCs can tell the difference between a dead body lying in front of it and an arrow that whizzed past their head and missed them. But it also helps ensure that things such as the player hiding in long grass or behind trees cannot be seen, given they recognize they are not visible in that state. Each eye character machine and human alike can handle and interpret sensory data in a different way, so certain information might be ignored by some characters, whereas others react to it promptly. In fact, depending on the strength of a sensor in a given machine, it can actually reduce the data from the sensory event that they can read. This helps manage the emergent properties of the game, such each character type responds to information in their own unique way. Now, should an eye make a decision based on this sensory data, we have still got to make sure it looks realistic. So when a machine has decided to make any action, such as moving to a new location, investigating a disturbance, or attacking the player, there is still the issue of animating it during execution such that it looks as realistic as possible. The animation of these machines is a big challenge, given that they need to be able to look like they are animal inspirations, but also have a distinct machine-like behavior at times. This requires both the navigation and combat systems to pay attention to the distance the machine is going to traverse on animation, to the chain that adjusts root bones of animations and warp them to suit based on the perceived distance and time it needs. This ensures that regardless of how far the machine is moving and how fast it is doing so, it can start the animation, move into the main part of the behavior, and then blend it correctly at the right time. This is important for things such as running to points, where the machine not only needs to slow down and stop at the right point, but it's even more relevant in combat. Many of the animations used for attacks have two distinct sequences. There's the wind-up, which telegraphs the attack, followed by the big finish where the damage is dealt. Horizon Zero Dawn uses a similar method to that discussed in my case study on the Eye of Doom, where the system controls the current locomotion of the machine. Glance movement are attack animations to suit at specific points and they ensure that the machine lands or stops in the right at the finish. Now, there is still one big issue I have not yet talked about, and that is navigation. Ensuring these machines can wander around the environment is a real challenge, given this large variety of unique enemy types of all different sizes and shapes. So they need to be able to move through terrain in a way that makes sense for them. But also, they need to be able to recognize changes in local geometry and adapt to that or simply ignore it depending on their type. Now, this requires a commonly used item known as a navigation mesh. A nav mesh stores information about how a given character can move across the map, based on what are perceived to be obstacles in the world. While you can calculate it at runtime, they are often built or baked before the game is released and loaded into memory when necessary. Given Horizon Zero Dawn has such a large map and only specific segments of it are relevant at a given point in time, since they are only active and moving around. If they are near you, the navigation mesh is built at runtime, but only around a limited region of the player. But the thing is, there is not just one nav mesh. There's 6 of them. 4 of them cater for character movement, based on the size of the object, small, medium, large and extra large. Hence humans can move around on the small mesh alongside witches, while the likes of the Thunder Job has a nav mesh pretty much all to itself. Plus the 2 extra nav meshes, one for swimming machines such as the Snapmore, as well as a unique mesh that ensures machines stand in good locations should the player be trying to mount them. In each case, obstacles can block or alter a navigation mesh structure, and the system recomputes changes in real time, such that moving obstacles and even other machines can impact the ability to move around the space. What's interesting about this is that obstacles have differing properties and can either prove to be completely impassable or simply undesirable to walk across. But much of that is dependent on the state of the machine's eye behavior. As mentioned in Part 1, machine patrols actively avoid stealth vegetation when generated, but when investigating local disturbances, while grass is still considered undesirable, it will walk through it if necessary. This same principle actually applies to small rocks and trees. These are impassable obstacles, except for larger machines such as behemoths, rock breakers and thunderers. These beasts can smash rocks apart and uproot trees, but only if they are in an angered state, or giving chase to the player. Outside of that behavior, they will treat them just like any other obstacle. While this navigation tool chain caters to land-based machines of all shapes and sizes, it does not work at all for those that are based in the air. Non-player characters that move through the air not only have to be aware of the nearby obstacles such that they do not crash into trees or cliff rock, but they also need to be wary of the elevation of nearby geometry. The world of Horizon Zero Dawn is full of rolling hills, forests, rock outcrops and steep mountain climbs. For the two flying machine types, the Glint Hawk and the Stormbird, they need to know how to navigate the air such that they can take off, fly a patrol route, land and also swoop down and attack the player when necessary. To achieve this, the game not only has the navmesh system on land, but a completely separate navigation system in the air. This proved to be a challenge for the AI team on the game. The technique used is known as hierarchical path planning over mid-maps. Mid-mapping is a technique used in computer graphics that aims to minimize the memory overhead of a texture or images by providing a collection of the same image, gradually lowering in resolution. It's ideal for monitoring level of detail in games so that objects hundreds of meters away can be visible, but use less textual memory than those directly in front of the player, where you need them to be the highest quality possible.